Hi everyone, this is Mr. Terence Chu again. I'm going to go through some examples, variations of a very basic example, and it actually helps to deepen our understanding of the use of two very basic equations but very important equations. There's path difference equals to n lambda, there's the condition for constructive interference, and path difference equals to n plus half lambda is the condition for destructive interference. Of course, you need to be aware that this is only if the sources are in phase. If the sources are out of phase, then it will be swapped around. And I'm going to incorporate this into the first example I'm going to go through today. Say, for example, if you've got S1 and S2, very simple example, probably you have seen this in our class before. So this is 12 meters away, you've got a screen, and I got a point M over here and a point X over here. Now, this information over here says that M is a minima. That means there is no sound. Say, for example, if it is a sound wave, there's no sound over here. So what can we deduce about the sources if M is a position where there is no sound or soft sound? So the thing that we can deduce over here is that if the path difference is 0 because it is a isosceles triangle over here, so the two sides over here are of the same length, so the path difference is actually 0, and path difference 0 falls under this category because n equals to 0 is also an integer. Therefore, it should be constructive interference, but over here it is a minima. So therefore, it tells us that the sources are not in phase. Therefore, in summary, whenever you want to check whether the sources are in phase or out of phase, very simple. You always look at the midpoint. Look out for this piece of information in the question, whether the source, the point at the center, whether it is a minima or whether it's a maxima. That will tell you whether the sources are in phase or out of phase. So if X is the third maxima, third maxima, let's put it at maxima. So what is the wavelength of this wave? Using Pythagoras theorem, we'll be able to know that this is 12 meters. 12 squared plus 5 squared will give you this, which is 30 meters. So the path difference is equals to 1 meter. Why so? Because it is 30 meters minus 12 meters. That will give you 1 meter path difference. So the question is, what is the wavelength? So if X is the third maxima, how does this help us understand what is the wavelength? Now, let us do some simple counting. So if this is minima, and if the first maxima over here is over here, then the path difference at that point, remember, if sources are out of phase, then the condition gets swapped around. So if the sources are out of phase or anti-phase, then this would be destructive and this would be constructive. So if it is a maxima at this position, the first maxima, then the path difference over there must have been half lambda. 0 lambda minima, half lambda maxima. And if it is 1 lambda, it is a minima. So the next point over here will be a minima, where the path difference is equals to 1 wavelength. And if it is the point where the path difference equals to 1.5 wavelength, it will be the maxima, another minima, and then X will be the maxima. So if this is half, 1, 1.5, 2, this will be 2.5 lambda. So what am I trying to say over here? When you see this kind of information, you need to translate to this kind of information and relate to the physical path difference. Then you'll be able to see that the wavelength is 40 centimeters. That becomes really easy. So at this point of time, I'd like to do a quick summary of the 2 points that you need to know. First, look at the center. That will tell you whether the sources are in phase or out of phase. If it is a maxima, the sources are in phase. If it is a minima at the center, then the sources are out of phase. Then that will have implication on the conditions over there. Then the next thing that I need to remind you is you need to translate this information into the path difference in terms of wavelength. So don't worry, you will not be given a question where it's like the 29th maxima or 29th minima. Usually questions will hover about the first to the third roughly over there. So you don't have to worry too much about the counting. So do some simple counting that will take you at most about 15 seconds more, probably to 20 seconds, and it's worth that counting. All right, so this is what I need you to know. Now I'm going to go into the different variations of questions. Let's use exactly the same example so that we have minimal change mathematically, structurally. Then we talk about what sort of conceptual change or things that you need to look out for when the question is tweaked. So S1, S2, the same thing, 5 meters, and I got a screen over here, there's 12 meters. And I start walking from this point M, which is a minima that is mentioned just now, and I start walking to infinity, assuming that I can still hear the sound source, which is a very hypothetical situation. So if we can hear the sound, even if we are very far away, how many maximas will I go through? Remembering that the wavelength, we found it just now, it is 40 centimeters, which is 0.4 meters. At this point of time, probably you want to press pause and think about this question. How do you find the maximum number of maximas? A hint for you is to think about what is the maximum path difference. Remember that when we went from here, the path difference starts to increase from half lambda, one lambda, 1.5 lambda, 2 lambda, 3, and then there will be, if there is a maximum number of maximas, then there should be a maximum path difference. So where is the path difference? What's the situation when the path difference is the maximum? You see that as I move from here to here, move from here to here, the path difference starts increasing. Why? Because we went from 1 lambda, 2 lambda, 3 lambda, 4 lambda. So the path difference must be increasing as we go here. So the maximum path difference is when we go here, when we go vertical. So can you see that the path difference is 5 meters? And therefore, the path difference equals to 5 meters over here. And if you take it to be equals to k lambda, k over here will be equals to 5 meters divided by 0.4, it will be 12.5 wavelength. So the maximum path difference will give you 12.5 lambda. And remember, if it is half lambda, it is the first maxima. 1.5 lambda, it will be the second maximum. 2.5 lambda will be the third. So if it is 12.5, then there will be 13 that you will detect that. But that's of course, when you're so far away, you still can detect the maximum. But of course, we're talking about the hypothetical situation where you still can detect signal. All right, so what should you learn from this example? Whenever you see the word maximum number of maximas or maximum what, you need to translate the information into what limits the maximum number of bright spots or maximas that can detect. In this case, it is the path difference. Then you translate it into something. What is the situation where you can get the maximum path difference? And then what is the maximum path difference? So you need to be able to translate information into other forms so that you can relate eventually back into the setup itself. Okay, so the question, just a summary, the question is find the maximum number of maximas that I can detect as I move here. And the way to do it is to think about what about the setup limits the maximum number of maximas. And the answer over here is path difference being 12.5, and therefore you should detect 13 maximas. All right, this is the first variation. Second variation, same example, same situation, but I'm going to tweak it another way. That's why I really love this example, because I can tweak it so many different ways, and yet each of them packs inside certain learning points. So let's consider point X now. Reset the setup, everything the same again so that we reduce the need to do any more calculation. So everything the same, M is a minima, X is the third maxima. Now what is different is that I got the source S1 over here starts to move backwards at a speed of say 1.2 meters per second. So what the question basically is, find the rate of change of intensity at point X. Find the rate of change of intensity at point X. Probably at this point of time, you'd like to think about what caused the change in intensity. What caused the change in intensity? Because if you can detect, if you can find that change in the cause for the change in the intensity of X, then you might be able to find some hints as to how to relate the 1.2 meters per second to the answer that you need to find. So what caused that change? Probably like to press pause right now, and before I go on to explain further, and think about the question that I asked you. Alright, I hope that you are able to identify the way to get the answer. If you haven't, no worries, this is why I'm here. I'm going to explain to you how to go about this question. So the way to go about this question is, when this source moves backwards, how does the path difference change? This doesn't change because it is the same position. X doesn't move, it's this that moves. So the path over here doesn't change, it's 30 meters. Now, do you agree that as this moves backwards, the path difference is changing? Say if this is y and this is z, do you agree that the path difference is y minus z? If this is not changed and this is changing, then this must be changing. And do you agree that every time S1 moves back by 0.4 meters? Why is that important? Because the wavelength is 0.4 meters. Every time the source S1 moves backwards by 0.4 meters, the path difference will change by 0.4 meters. It will change by 1 wavelength. Remember that we mentioned that this is third maxima, so this is 2.5 wavelength. So as S1 starts to move backwards by 0.4 meters, this will drop to 1.5 because this length increases by 1 more wavelength, and therefore this will drop to 1.5. Another 0.4 meters backwards, half. Another 0.4 meters backwards, it will be this bigger than this by half already, not the other way around. So every time it moves back by 0.4 meters, there is a change from loud to soft to loud. So therefore, the question becomes, how many 0.4 meters does it go through in a second? All you need to do therefore is taking this divided by this, you get 3. So every time it moves by 0.4 meters, it goes from loud to soft to loud. So therefore, if it goes through 3.4 meters every second, then it should have gone from loud to soft to loud 3 times every second. So the rate of change of intensity at X is 3. Alright, so let's rewind and find out what's the thinking process. The question was, find the rate of change of intensity at X. So we relate, why is there a change in intensity at X? There must be, back to the conditions that we learned just now, there must be a change in path difference, because the only thing that determines whether it goes from loud to soft is the path difference. Since the wavelength didn't change, it must be the path difference that changed. And how did the path difference change? The only thing that changed is the distance z over here. So then you think about what changes in the path difference allows it to go from loud to soft to loud. So therefore, it must have gone through a 1 wavelength path difference change to go from loud to soft to loud. And therefore, every time it moves backwards by 0.4 meters, you go from loud to soft to loud. And therefore, the question becomes, how many 0.4 meters it moves by? It moves through every second, and therefore it's 3. Alright, so this is the question. The second variation. The third variation is going to be also equally interesting. I think it's one of the more difficult variation. Let's take a look at this one. Same thing, 5 meters, 12 meters, still at X. And this is the M, same setup, minima, and this is the third maxima. So the path difference, the same thing as we did just now, 2.5 wavelength. The wavelength is 0.4 meters. Okay, so what I am going to change right now is the frequency of the sources. So what I'm going to change is, I'm going to increase, when I increase the frequency of the sources, the frequency is increased such that X undergoes 2 cycles of intensity change. So the task for you is find the new frequency. So the previous frequency is, okay, I realize that I haven't given you the speed of sound. So say for example, the speed of sound is 300. Let's keep the math simple. So it's 300 meters per second. So the frequency is just 300 divided by 0.4. That's times 2.5. So that's 750 hertz. So the previous frequency is 750 hertz. So what is the new frequency? It must be higher because I increased it. So probably at this moment of time, you may want to press pause, give it a try if you want to, before I show you some hints and how to solve the problem. Alright, I hope that you are able to come up with something at this point of time. So the question is, how does frequency change the scenario? Now, let's keep this in mind that the previous frequency is 750 hertz. So let's take a look. Path difference equals to 2.5 wavelength. That was the previous scenario. Did the path difference change if it is point x? No, right? So it is still this minus this. No change to the path difference. So the 1 meter here hasn't changed. Now when I change the frequency, when I increase the frequency, the speed of sound doesn't change because speed of sound depends on the nature of the environment, its temperature, the density, the humidity. It depends on the nature of the medium. So the speed of sound doesn't change, and if I increase the frequency, V equals to F lambda, when this increase, this must fall. So if this fall, what do you think will happen to this? So this will increase. So every time it goes from a half lambda to a maximum, the lambda starts changing, decreasing, and therefore this increases. When it hits this one, it's a minima. When it hits this one, it's a maxima. When it hits this one, it becomes a minima. And when it hits this one, it becomes a maxima. So this is a max, minimum, max, minimum, and max. So the question I gave you just now is that it went through 2 cycles of change. Therefore, it goes from here to here 1 cycle, goes from here to here 1 cycle. Therefore, you need to recognize that the path difference is still 1 meter, but this is the one that changed. Therefore, from here, you'll be able to find the lambda 4, which is the lambda final, is equals to 1 divided by 4.5, which is not that friendly a number. But if you define the frequency, it will be 300 divided by the wavelength, which is just times 4.5. Because 1 divided by 4.5 will be times 4.5. And this will give you, I think, 1350 hertz. So that's the new frequency. Alright, so this is a very interesting change because usually we talk about the change in path difference over here when the thing moves, right? The first 2 examples, this change. But now we talk about this change to adapt to this change so that this is still 1. So you need to be able to understand what part of this condition is the one that changes, which is what is tested in this example over here. And the last tweak of this setup over here is this. And I will give you the scenario, I will show you what happens, and I will urge you to think more about this example, and I'll offer you some perspective. So let's take a look at this case over here. S1, S2. So we got minima, maxima, minima, maxima, and so on and so forth. Yeah? So it's a series of maximum, minimum, maximum, minimum. So if we move the screen closer and closer, do you agree that it will still be the same? There will be maximum, minimum, maximum, minimum, maximum, minimum, maximum, minimum, maximum, minimum, maximum, minimum, maximum, minimum. But doesn't it mean that if we were to move that line to here, if we were to move the microphone, if we have a microphone up and down, don't you agree that there will be positions of maximum, minimum, maximum, minimum, maximum, minimum, maximum, minimum? Right? So it's the same. I mean, you're just moving the screen closer and closer. So what we have over here are 2 waves that moves in opposite direction. They meet and superpose. Quite different from what we have over here where the wave moves outwards. In this case, the wave moves towards each other. So what we have over here is actually something called standing wave. And that will be the next lesson that I'll be recording and uploading for you to learn from. standing waves, or we call it stationary waves. We're going to talk about the nature of it, how is it different from progressive waves, and some of the things that you need to know about ways that we produce different kinds of standing waves. All right, so enjoy. Just a quick recap. I went through the one example, but four different kinds of different scenarios out of it, and each of them tests your ability to decipher, to digest the question, the information, and to translate it back to the most important condition that we talk about, that is the path difference equals to n lambda, path difference equals to n plus half lambda. All right, so take care. Hope that you will understand this better from this lesson. Thank you.